So in this section we will learn about comparison of f prime, the derivative of the function and the function itself, and the second derivative of the function with the function. So the topic is, what does f prime say about the function f? So you are given a function f, and if the derivative f prime is greater than 0, which means the derivative is positive on an interval, then the function should be increasing on the same interval. So you can write increasing. If f prime, the derivative of the function, is less than 0, then the slope is negative. If the slope is negative, then the function should be decreasing on the same interval. But what suppose if f prime, the derivative, is equal to 0, which means the function is constant on that interval. You can draw a horizontal tangent at that point. So here we have a graph with all these characteristics. Let's mark it. In the first place, I want you to write here f prime, the function, is greater than 0. So equivalently, you are seeing that the function is increasing. On this part of the graph, you are seeing that f prime is negative, less than 0, slope is negative. So equivalently, it's okay to say that the function is decreasing. And here at this point on the graph, all you're seeing is f prime is equal to 0. So an equivalent statement would be to say that the function is constant at this point, at all these points. In the next example, you're given a graph of f prime and you want to see how the function graph look like. So it's also known that the functional value 0 is 0. So you want to sketch a possible graph of function f, where you're given a f prime graph. So read your f prime graph carefully. The y-axis is not the usual typical y-axis, but you want to read it as f prime graph, f prime axis. And this graph is specifically f prime graph, so it's not the function graph. So all this goes on how well you can read the graph. So let's read the graph. From the interval negative infinity to negative 1, on this interval, you see that the functional value is increasing. You see that the slope of the function is increasing. So you can say negative infinity, negative 1, f prime is greater than 0, and you can say that the function is increasing in this interval. And then you move on to the right hand side. Say from 1 to infinity, in this portion of the graph, 1 to infinity, the function f prime is still positive. So correspondingly, you can say the function is increasing. And between negative 1 and 1, you read the values here, the f prime values, it's negative. All these are negative values. So they are negative values of f prime between negative 1 and 1. So you say that the f prime is negative, and then you say that at x equal to 1, you have f prime 1 equal to 0, and here at x equal to negative 1, you can say f prime negative 1 is 0. So you read the graph carefully. All the values above the x-axis, all these values above the x-axis are the positive values, and all the values below the x-axis are the negative f prime values. So you had two pieces of the graph, negative infinity to negative 1, 1 to infinity above the x-axis. So you are specifically saying that the slope is positive there. But between negative 1 and 1, you are seeing that the graph is below the x-axis. So you say that the f prime, the slope is negative. Above the x-axis, slope is positive. Below the x-axis, slope is negative. So once you have read all these curves carefully, you're all set to do a graph now for the function. So let me do a function graph. The y-axis here is f of x. So you're trying to plot a function of x graph here. So in this example, you were given an f prime graph and you're asked to do an f function graph. So at mark -1 and 1. So at -1, you have between -infinity and -1, you have the function to be increasing. That's what we stated here. So from -1 infinity to -1, you want to draw an increasing function. -1 to 1, you see that the f prime is decreasing. If f prime is decreasing, the function should decrease. So between -1 and 1, you want to draw a graph which is decreasing. Then from 1 to infinity, you have a function with a positive slope, which means the function is increasing. So now you want to draw an increasing graph. You also try to make sure that the graph passes through f0 at 0, because you are given that the function graph passes through f0, 0. And you are able to draw a horizontal tangent at -1 and 1, because you have f prime -1 is 0, f prime 1 is 0, which means at -1 and 1, the slope of the function is 0. So we have all the characteristics from the f prime graph, which has been transferred to the function graph, which still holds the same definitions as the f prime. So you want to write this as the local max, and this is your local min, and this is your function graph. Next, you have a definition. Suppose x equal to c is in the domain of the function. If the f prime changes from positive to negative at x equal to c, you call f of x is a local max. We did see this in the previous example. The function has a positive slope here and negative slope here. So at this point, it's changing from positive to negative, which means the function is local max. Similarly, f prime changes from negative to positive at x equal to c, so the function will be local min. Next, determine the local max and the minimum value. So you read the graph and then you say the max and the min. So at -1, you see a maximum here. So you write at x equal to -1, you have a local max. And at x equal to 1, here at this point, you have local min. So these are just reading the graph problems. One more graph, you want to list the max and the min. Now read this graph carefully. In the previous graph, it's a function graph, but this is a f prime graph. So when you read the y-axis, it's not the usual function, but it's the derivative f prime. And this graph here is not the function, but the derivative. So you want to carefully note f prime graph at points where positive to negative, where f prime changes from positive to negative, you call that particular point to be local max. And when f prime changes from negative to positive, that particular point is called as local min. So now let's read the point x equal to 1 carefully from the graph. At this point, you see that the f prime values are negative here and it's positive here. So at this point x equal to 1, f prime changes from negative to positive, which means you should have a local min. So let me write f prime of x changes from negative to positive at this particular point. So x equal to 1 is the point at which you will have a local minimum. The local minimum cannot be read directly from this graph because this is an f prime graph. Suppose you are doing an f function graph from this f prime graph after transferring all the definitions, then the local min at 1, say this is x equal to 1, you would see a local minimum like this. This is your minimum value. You can see this minimum if it is a function graph, whereas the given graph here is an f prime graph, so you're not able to see the minimum value. But you can match the definitions to find out the minimum value. Next, you want to carefully observe the point x equal to 6. The graph here, when you read the graph, you always read from left to right. So it was positive above the x-axis and becomes negative below the x-axis, the f prime value. At 6, this positive to negative is changing the sign. So you want to write at x equal to 6, the f prime function, which is the graph, is changing from positive to negative. So when the slope changes from positive to negative, that particular value at x equal to 6, you will have a local maximum value. Again, you're not able to see the maximum value directly from the given graph because this is an f prime graph. Had you drawn a function graph, then you will see at 6 you have the maximum of the function. One more definition. At x equal to 8, you want to again observe that the graph changes from negative to positive. So you want to write f prime changes from negative to positive. So at exactly x equal to 8, you can say that you have a local minimum. So when you draw a function graph, you will be able to see a minimum value at 8. So this is at 8, you will see the minimum value. Next is the definition of concave upward and concave downward. If f double prime is greater than 0 on an interval, then the function is said to be concave upward. So you're trying to relate the f double prime with the function definition. So what does f double prime say about f? That's the topic. If f double prime is less than 0, then the function will be concave downward. Concave upward will look like an open up curve. Concave downward is an inverted cup. So f double prime equal to 0, then the function is constant on that interval. And you can also say that when f double prime is equal to 0, x is the inflection point. So you are given a graph here. I want you to observe this graph carefully. We have a tangent at this particular point. So let me draw the horizontal and the vertical line to make it look like a triangle. Well, the idea is we want to discuss the slope of this function here, f prime x. It's seen that the f prime x is increasing at this point, so you can write greater than 0. When f prime x is increasing, you say that the function is increasing. At the same point here, observe the shape of the curve. Let me redraw it. So at this point it's going up, so it's concave upward, and at this point it's going down. So you want to observe such a pattern of the curve to say that whether you have a concave up curve or a concave down curve. But here we are observing the pattern of the curve is this, so it's concave upward. So we can say f double prime is greater than 0. And in the second curve, at this particular point here, I would want you to observe the pattern of the curve. It's going down in this pattern. So this particular curve on this interval, you can say that f double prime is less than 0. And this is the concave down curve. So concave up and concave down, you should be a little careful about the pattern of the curve to say that whether you have the second derivative positive or the second derivative negative. And if you are finding the inflection point, you know that you want to check the point where the f double prime is equal to 0. So in the next example, on what intervals is the function p a concave upward or concave downward? So the graph is the graph of the function p. Now I want you to observe this particular pattern of the curve which goes like this. I'm redrawing this curve, it goes like this. So if you try to finish this curve on the left, we are not sure what's going to happen. But if we give a nice shape, this might be a concave upward curve. So just studying this pattern here, we say that this is concave upward curve. And then 12 will be the inflection point because you're seeing the change in the pattern of the curve. And then you want to study this particular pattern of the curve, which looks like half of the concave downward curve. So if this is your concave downward curve, half of the curve looks like this. So this is your concave down. So concave down, f double prime is less than 0, so you can say f prime is less than 0. Concave up, f double prime is greater than 0, so you can also say f prime is greater than 0. So now let's do this exam definition. Inflection point is approximately when t is equal to 12 from the graph above. And this is the point where the curve changes. There's a typo here, please correct it. Its direction of concavity. So it's changing from at 12, it's changing from concave up to concave down. So that particular point is called as inflection point. Now in the next example, you want to use the graph below to sketch the graph of the function f. The graph given is an f double prime graph. So read the graph carefully, mark these endpoints as A and B. And when you read the y-axis, it's not a typical y value, but it's a f double prime value. So let me say that f double prime, the second derivative, is going to be positive. Then you say that the function f is concave upward. And the shape of the concave upward is like this. And then you say f double prime is less than 0, second derivative negative, if the function is concave downward on that particular interval, which means you can expect to see a downward inverted cup shape of curve. Or f double prime is equal to 0, which means this is an inflection. This will lead you to discussion of inflection point, whether concave up to concave down or concave down to concave up, which means there's a change of concavity. So let's read the graph carefully and let's list all these definitions to answer the question. F double prime here in this problem is greater than 0 on the interval negative infinity to a, which means this is the concave upward curve when it comes to a functional curve. But how did we decide that f double prime is positive? You read this particular values of the curve from negative infinity to a, so at all these values, the graph lies above the x-axis. Above the x-axis is positive values, and it's a positive values for f double prime. Similarly, you want to read the graph between a and b, f double prime. So between A and B, you see that the curve is this one, and all the curve values are negative. So you can say f double prime is negative. And you say the curve should be concave down, the function should be concave down. When you list the intervals and the f double prime, all you can say is what happens to the function at the same graph, same interval. F double prime x is greater than 0 on the interval, say b to infinity, and you see that these values are positive, so you can write they are concave up. And at 2 points, exactly A and B, you're seeing that the graph touches the x-axis, which means you can say f double prime A and f double prime B both are equal to 0. If they are 0, all you can say is they are inflection points. So with all these definitions, let's try to do the graph of the function. If you want to do the graph of the function, what you want is these two columns, the intervals and how does the function behave in those intervals. Negative infinity to a, so mark AB, the function is concave up. So you want to draw a concave up curve. You can draw only half of a curve. And then from A to B, it's concave down. So you bring down the curve. And then from B to infinity, it's concave up. So you rise up the curve. So you're seeing a concave up curve here, concave down curve here, and again a concave up curve here. Still the function is continuous, and at a and b you should have a flat curve, which means the derivative should be 0. And there should be a concavity in the curve, which means concave u, concave upward is changing the sign positive to negative, concave down to concave up, negative to positive. So you should be able to see the change of sign at these 2 points, which are the inflection points. So with all these definitions, let's try to do this graph. In this example, you are asked to sketch the graph of the function that satisfies these definitions. So with the definitions, you will be doing a function graph. So read the first point carefully, f prime 0, 0, f prime 4, 0, which means these are the definitions of horizontal tangents. The meaning of horizontal tangents, at 0 and 4, you should have a flat curve. So as soon as we read the definitions, let's try to mark them. This is 0 and this is 4. So at 0 and 4, when you draw the function graph, the slope of the curve should be 0, which means you should see a curve which is flat at 0. Say if it's going down, you should see a flat curve at these 2 points. In the next definition, you see that f prime is greater than 0 if x is less than 0, which means for all the negative x values, this is the values x less than 0. In this part of the curve, you should see the function has a positive slope. If the derivative is positive, the slope is positive, all you can say is the function is increasing on the same interval. So the graph should go up or increasing. Then you move on to the next definition. F prime is less than 0 on the interval 0 to 4. So 0 to 4, that is this interval, this is 0 less than x less than 4 interval. The f prime at 0 should be less than 0. So the slope is decreasing. This should not be f prime 0, but this is a typo. It's just f prime is less than 0. So slope should be decreasing at this interval. If the slope is decreasing, if you try to draw the function graph is decreasing. Then for all x greater than 4, so it's all these values, it's it's still the same definition. F prime is less than 0, which means the function should go down in this part. So we are done with the second line of the problem. Let's move on to the third line definitions. Between 2 and 4, you should have f double prime greater than 0, which means it's concave up. So this is the definition of concave up. So between 2 and 4, now you want to mark the point 2, 4. Say between 2 and 4, you are having a concave up curve like this. And if x is less than 2 or greater than 4, so it's all these x less than 2 and greater than 4, at these points you should have f double prime less than 0, which means this is the concave down on these intervals. So when you draw a final curve, your curve should look like this. Any piece of the curve you draw on these intervals should be having a shape of concave down. So let's use all these definitions, try to connect them to make one single nice smooth graph, continuous graph. So on the first interval, less than 0, x less than 0, you have the functional graph to be increasing. The function is increasing. So let me draw an increasing graph. At 0, you have the slope 0, so the curve flattens up. It's a horizontal tangent. And between 0 to 4, you have the functional values going down because the slope is negative. So you should draw a curve which is going down between 0 to 4. Again, when you come to 4, you should have a flat curve, but again the curve should still go down. But also when you finish drawing this with all the f prime definitions of function going up or function going down, you still want to compare with your f double prime definition and alter a graph little bit if required. So let's check our f double prime definition. For x less than 2, we should have concave up, and you are seeing a concave up. Sorry. You're seeing a concave up shape here. For x less than 2, the shape of the curve is like this. So it's almost 3/4 of the concave up curve. I'm sorry. For x less than 2, you have concave, this is concave down. For x greater than 4, it's a concave down curve. So for values between 2 and 4, you have concave up curve. So let me write, between 2 and 4, you should see a concave up. So first, let's check the concave down curve. For x less than 2, you're seeing the pattern of the curve goes like this. Until 2, it's like this. So you're seeing almost 3/4 of the concave down curve. So it's correct. X greater than 4, you're seeing a curve here. For x greater than 4, this is this part of the concave down curve, the last few values of the concave down curve you want to compare with this pattern here, and for this concave down curve you want to compare at least 3/4 of the curve. Now between 2 and 4 you should have a concave up curve, so you study the pattern carefully and you're seeing at least half of this curve here. So you don't want to redraw the graph. It's almost matching with the definitions in the given problem. So using the definitions of increasing decreasing function, concave up, concave down, you're able to sketch the graph. So let me erase all this. But I want you to compare each of these pieces with this pattern of the curve.